This is a continuation of the lesson that we started yesterday on waves and vibrations. Yesterday we went over Hooke's law. So Hooke's law is defined by the equation F of S is equal to negative kx, where this is a restorative force, so it's always working opposite to the motion or to the direction that an object may be in. So if it's going to the right, the restorative force wants to go to the left. If it's going to the left, the restorative force wants to go to the right. Okay. Then we went over 3 more terms. We went over frequency, amplitude, and period. So period is t, and it is defined as the time that it takes for a system to complete one cycle. Frequency F is the time or how much of a cycle is completed in 1 second. And lastly, it's amplitude A. That just refers to the maximum displacement from equilibrium that a system has. Okay. As you guys may remember, period and frequency are related to each other by being reciprocals of each other. And today we're going to be covering a very important topic that we call elastic potential energy. Okay. So you may have heard of other types of energies in your other physics classes. Maybe you haven't. But in case you have, you may have heard of kinetic energy, which is equal to 1/2 mv squared. You may have also heard of gravitational potential energy. That's just equal to mgh. And then lastly, we have what we're going to be covering today, which is elastic potential energy. We write it as U sub S, and that's equal to 1/2 kx squared. And so whenever a spring is oscillating back and forth, and again, oscillating is anything that repeats its motion over and over again, it's gonna have both elastic potential and kinetic energy. So as you'll see here, this is just a spring block system where the block is at x is equal to 0. So when x is equal to 0, you can see that elastic potential energy is also going to be equal to 0. Because if you plug in 0 for it, there's nothing. There is no displacement. But if we grab this system and we stretch it to its maximum displacement or its amplitude at A, where x is equal to A, then we're going to have the maximum possible elastic potential energy. Okay, where we plug in A for x, and that's because A is our amplitude and our spring cannot stretch past A. When x is at A, that's going to be our maximum value. And we can write that equation as 1/2 kA squared, where x is replaced by A for its amplitude. So when this block is pulled to A and then it's released from rest, it's going to shoot back towards the left because there's a restorative force making it go back, and then it's gonna reach equilibrium, right? But because it's going towards the equilibrium with a velocity, it's actually going to overshoot and go to the other amplitude on the other side, the negative A. And then when it gets there, because it's compressed, it's going to want to stretch back out. And then it's going to go back towards equilibrium and overshoot again and go back to A. And that's what we call this oscillating motion, where you have this spring block system that keeps rotating from being at maximum displacement on the right side to equilibrium to maximum displacement on the left, and so on and so forth. Okay, and now I mentioned that as it's going towards equilibrium, it has a velocity, and because it's a block, it has a mass. And as I've mentioned in other lectures, whenever you have mass and velocity present, you have kinetic energy present. So that means that as this object is oscillating back and forth, you have both elastic potential and kinetic energy present. And what we're going to be doing is we're going to be looking at how we can determine which energy is present when and what their values are. And this is going to be done by following specific rules that follow. And what I'm about to write down is very important, so I recommend that you guys pay attention to it and write it down. This has to deal with conservation of mechanical energy. Okay. So when a spring is at its maximum amplitude, either at A or negative A, there are certain properties that occur. It actually has zero velocity, and it has maximum elastic potential energy. Okay. So that's one of the situations that we're going to be looking at when a spring is at its amplitude, at its maximum displacement. The second one is when the spring is at equilibrium, is at the equilibrium position or passing through it. It actually has maximum velocity and zero elastic potential energy. And this should make sense to us because as it's passing through equilibrium where x is equal to 0, we expect it to not have any elastic potential because x is equal to 0, and plugging that into our equation would give us 0 for a value. Now what I'm going to draw here is actually how total mechanical energy, kinetic energy, and elastic potential energy are related to each other visually in the graph. So on the x-axis we're gonna have the position, and on the y-axis we're gonna have the energy magnitude, or just the energy levels. Okay, so on the left side we see we have x is equal to negative a, and on the right side we have x is equal to a. So those are the amplitudes, so our values are going to stay within those boundaries. They're not going to go past it. Okay. Now, when we're talking about conservation of mechanical energy, what this means is that no matter what is going on, our mechanical energy is going to be equal throughout the whole thing. And what does this mean? It means that if I add up the kinetic and potential and elastic potential energy at any point, they're always going to be equal to the same value. That's what total mechanical energy is, and that's what that first line that I drew across indicates, is that no matter where we are, the total mechanical energy is staying constant throughout the whole system. Okay, now we're going to start off by analyzing what the elastic potential energy will look like. And we do this by looking at the statement that I had written and just thinking about it. So it says that when a spring is at its amplitudes, it has zero velocity and maximum elastic potential. So we already know where to plot 2 points of our graph. Where x is equal to negative a and x is equal to a, we know that elastic potential is at its maximum. And that means that kinetic energy is zero because velocity is zero. So elastic potential has to equal the total mechanical energy at that point. Okay? And now, using the second sentence of that statement, it says that when the spring passes by x is equal to 0, it has 0 elastic potential and maximum velocity. Okay? So, simple enough. When x is equal to 0, elastic potential is equal to 0. As you can see, I write down the equation once more. That way it is very clear visually that if x is equal to 0 and you plug that in, all that equation has multiplication, so multiplying by 0 will result in 0. And now for everything in between, we can just graph it, or we do a sketch to represent it. We know that it's a quadratic graph, so it would look something like this. And as you can see, it shows you that as you're approaching the equilibrium point, your graph actually slowly gets to 0 value, and then as it goes from equilibrium back to an amplitude, it starts to shoot straight up and increase in value not exponentially, quadratically. Okay, so now in blue I'm going to sketch what the kinetic energy would look like. Okay, so kinetic energy is 1/2 mv squared. Okay, so again, we can stick to the statement above and start sketching our graph. Okay, it says that whenever we are at a maximum amplitude, right, when a spring is at its amplitudes, it has 0 velocity. So similarly, we can just label our kinetic energy or plot our points at 0 when x is equal to a and negative a. And then when x is equal to 0, we actually have a maximum velocity. So that means that at that point there is no elastic potential, as we just saw. So that means all the energy has to equal the total. All the total mechanical energy is purely kinetic energy at that point. And again, we sketch it because we know it's a quadratic graph. And what we see here is that, let's say you take any 2 points, or not any 2 points, but 2 points at the same x position. Those 2 points should add up to the total mechanical energy, as I'm showing here. So for example, let's look at where the graphs intersect right there. Let's say that the total mechanical energy, like at that point, the energy is equal to 5 and the total mechanical energy is 10. right? So, because total mechanical energy is the sum of kinetic and potential energy, you would add up the kinetic and the potential. So, for example, at that point, kinetic is equal to 5, elastic potential also equal to 5. So, they add up to 10. When x is equal to 0, elastic potential is 0, kinetic is 10. So, 10 plus 0, 10. So as you can see throughout the whole graph, this should be true. When you add up the values at the same x coordinate, you should expect them to add up to the total mechanical energy. Okay. So what I'm gonna write here is the general equation where 1/2 mv squared is our kinetic energy, 1/2 kx squared is our elastic potential energy, and the sum of these two equals our total mechanical energy. Okay. So again, this is just me explaining that same concept where at certain points, all of the total mechanical energy is made up by only kinetic or only elastic potential when the other one is not present. And what this allows us to do is actually create this equation right here, where the sum of the mechanical energy, the kinetic and elastic potential at any point should equal the value of elastic potential when the spring is at its maximum, at its amplitude. Why? Because when the spring is at its maximum amplitude, that is equal to the total mechanical energy. And we're gonna explore that a little more in a practice problem. But I just want to slightly touch up on this topic that we call work. So work is present whenever conservation of energy does not occur. And this happens whenever we say something like, oh, energy is lost due to heat or due to friction or due to sound. Okay? But I just want to lightly touch up on it. We're not actually going to get too deep into it in regards to math and stuff like that. That's not what I'm going to require of you. But just know that there is a situation, or there's many situations in which conservation of energy does not work. And I mean, does not work. And that is because of work. But yeah, like I said, we're not going to be focusing on that. That was just something to, like a little side note. Okay, so this is I wanted to make a practice problem. That way it kind of reinforces the ideas that I introduced to you. So here we have a spring with a spring constant value of K is equal to 100 newtons per meters is attached to a block of mass 5 kilograms. if I stretch the spring to its maximum amplitude, or to its maximum displacement. Again, these terms are interchangeable when we're talking about springs. So if I stretch the spring to a maximum displacement of 2 meters, I want to find out all of these things. I want to find out what is the kinetic energy, or the maximum kinetic energy possible in this that this spring can store. I also want to find out what the velocity is as this block is going through the equilibrium point. Or the equilibrium position. And then finally, I want to know what the restorative force is equal to at x is equal to a over 2. And a over 2 is half of the amplitude, or half of the maximum displacement. Okay. So we're gonna take it step by step. We're gonna start off by figuring out what the maximum kinetic energy is. And now this should be fairly easy to solve using the equation that that you can see above that I introduced, because it says that the spring is stretched to a maximum displacement of 2 meters. So we know what our A is. We know what our spring constant K is. Okay, so this means we should be able to plug in our values to find out what our maximum kinetic energy is. Why? Because our maximum kinetic energy is going to be equal to our maximum potential energy. Okay, remember, energy cannot be created or destroyed. So if I have, let's say for example, 100 joules of elastic potential at one point, and some stuff happens, and at the end I have 0 elastic potential energy for some reason, it has to be transformed into something else. And in this case, it is transformed into kinetic energy. So that's why I'm able to just write K is going to be equal to 1/2 Ka squared. Again, because 1/2 Ka squared is equal to the total mechanical energy. And when I plug in for this, I have 1/2 of 100 newtons per meters times 2 meters squared. That's 50 times 4, and that is equal to 200 joules. Again, the unit for the SI unit for energy is joules. Okay, and that is our kinetic energy, or our maximum possible kinetic energy. And from before, this kinetic energy, or this value of kinetic energy, occurs when the mass spring system is passing through the equilibrium point, exactly when x is equal to 0. Not when x is like approaching 0 or it just passed it. It has to be at that very exact point. Okay, so with knowing this, we know that the maximum kinetic energy occurs at x is equal to 0, and the next question asks us what the velocity at that point is. So it's a very straightforward step from here. We know what the K is at that value, so now we just set this equal to 1/2 mv squared, and we start solving our equation for velocity. So first I multiply by the 2, then I divide by the mass. So it's 400 over 5. And then I take the square root of this. So 400 over 5 is 80. Then you take the square root of that. And you end up with the velocity being equal to 8.94 meters per second. Okay, so that means that's the maximum velocity that occurs when x is equal to 0. Okay, and lastly, it asks us what is the restorative force at a over 2. And this is very straightforward. Because it's the restorative force, we use the Hooke's law formula, where F is equal to negative kx. Now that we have this, we plug in our values. So k is 100, and x is equal to 2 meters. A is equal to 2 meters, so a over 2 is just 1 meter. So our restorative force is negative 100 newtons. This makes sense to us because the fact that it's negative makes sense to us because our amplitude is positive to the right, so our spring is stretched to the right, so our force wants to go to the left.